I thought it would be good in this example to show you how we could use Kirchhoff's current law in order to solve a parallel circuit, a circuit we've already seen and done a lot of practice with. So the first thing I'm going to do is I'll just fill in my chart with what I have. So I'm going to say that the total voltage is 5 volts. I know that R1, to start from the left, work my way out, it's 100 ohms, 56 ohms is R2, and 47 ohms is R3. Now the next thing that I'm going to do is I'm going to call the current through 100 I1. I call the current through 56 ohms, that's I2, and then the current through the 47 ohms is I sub 3. And I'm just going to call the current coming out of the power supply that total current. So that matches up with what we have over here. Now, because we have just a single wire here, the wires just connected together, it means we have no loss of potential on that wire. It also means that it's essentially one giant node. So all of this is essentially one big node because there's no loss of any charge because there's no resistors that are there. So I'm just going to call this our one node. And so if I look, I have the total current going into that one node. I have I1, I2, and I3 coming out of that one node. So that means if I were to use KCL, I have the total current equals I1 plus I2 plus I3. This rule should look familiar. This is one of those parallel rules that we have. However, what I'm going to do next is just take a look at what that really means and break it down a little bit. Now for I1, I know that I1, the current I1, is equal to the voltage drop across I1, so that's V1, and that's going to be divided by the resistance, so that's divided by 100 ohms. I know that for I2, again, just using Ohm's law, it's the voltage drop across that resistor divided by 56 ohms. And then for I3, it's just the voltage drop across that resistor divided by 47 ohms. And so if I just substitute in, I have my total current is equal to V1 over 100 ohms plus V2 over 56 ohms plus V3 over 47 ohms. Now, since we have a parallel circuit here, and since these are all just connected together, the potential is going to be the same all the way across the top because there's no loss of potential. So if we have 5 volts at the very top, because we have 5 volts of potential out of the power supply, we're going to have 5 volts everywhere at the top. There's no loss. There's no resistor to cause a loss in potential. Same thing at the bottom here. We have 0 volts at the bottom. Since there's no loss down here, that means everywhere across this entire bottom line, we still have 0 volts of potential. So the potential difference that we have, the voltage across all 3 of those are 5 volts, which makes sense because that's one of the things we knew from our parallel rules. 5 volts. This is showing you why those rules are in place, which means if I substitute in here, I know it's 5 volts divided by 100 ohms plus 5 volts divided by 56 ohms plus 5 volts divided by 47 ohms for my KCL equation, which means I can now find my total current. So I can just do 5 divided by 100, which is 0.05. So 0.05 amps plus 5 divided by 56, which is, I'm going to round out, I'm going to only round I'll round to 4 decimal places here, 0.0893 amps. I would round more. When you're doing this problem on your own, I would actually round out to more than that. I would just use the value from the calculator and just keep using that again. Then for the last one, 5 divided by 47 is 0.1064 amps. So if I add this up, I'll get my total current. So 0.05. In fact, I'm just going to use those values from the calculator just to get a more accurate answer. I get 0.2457 amps if I round that to 4 decimal places. So I know that 0.2457 amps is my total current, which means that if I wanted to find the individual currents, I've already found those just from my calculation inside KCL. So I have 0.05 amps, I have 0.0893 amps, and I have 0.1064 amps. And the last thing I need to do is just find my total resistance. To find the total resistance, I'm just going to use Ohm's law. So 5 divided by 0.2457. In fact, I'm just going to use what I already had in my calculator. I will get a total resistance of 20.353. This one I'm just going to round to 3 decimal places. 20.353 ohms. That's my total resistance. That's basically it. You could do the same approach using the parallel rules, but if you have trouble remembering some of the different rules, I just want to show you that KCL does apply. You can use KCL to solve a problem like this. I also wanted to show you that KCL is actually how you derive some of these parallel rules. In fact, if you look at the fact that V1, V2, V3 are the same, if you were to factor out a V, you'd have V times 1 over 100 plus 1 over 56 plus 1 over 47. That's where that resistance rule actually comes from. So KCL is actually how those parallel rules were derived in the first place.